Welcome everyone to the second to last class on Lean for scientists and engineers. We've come really far and I'm excited to see what we all build with this. So we are really at the final stage, provably correct programs for scientific computing. And today, as promised, we will be introducing LeanMD and LeanBET and sharing the progress we've been making in the Adams Lab on the two main applications that we've been building this out first. Tomorrow we will have a tutorial on Silene by Tomas Scriven. And so we'll start with a recap of the main points, and then we'll get into LeanBET and LeanMD, and finally discuss what you want to build. So in lecture one, we were talking about these different kinds of errors that we can encounter in scientific computing. And there are syntax, runtime, and semantic errors that are increasingly difficult to catch. And the goal of Lean would be to catch all of these at the editor phase. So we have proofs, and we're confident that we don't have any errors before we compile a program. Syntax errors, that's kind of common in every editor. Runtime errors, we talked about structured recursion and functions versus partial functions, the halting problem, and how Lean can essentially teach us. It's how we can use Lean to obtain proofs that we won't get any runtime errors in our code. And semantic errors are trickier, and we spent a lot of time talking about syntax and semantics. This is largely driven by, can we define scientific theories? Can we state properties about the functions in our code and then prove those things in Lean? Importantly, we're not addressing floating point or runoff errors. That is outside the scope of this course. And this leads to an alternative vision for bug-free scientific computing. The idea is you don't just write programs and tests and run the tests and make sure that your program is passing them. We can write specifications. And so this can be standalone properties of individual functions, or it can be theorems about how multiple functions and propositions and other objects in the code interrelate with each other as they should, according to our knowledge of science. And after doing all of that, then we have confidence that the code is mathematically correct. And this connects to syntax and semantics, being Lean by itself is designed to bring in logical syntax into type checking, so that when you are writing code in Lean, you are writing logical statements, and Lean is constantly checking and ensuring that the logical syntax of those is correct, and it will essentially do this filtering for you. All possible combinations of symbols instead becomes Lean guarantees that we have only logically valid statements are covered. But scientific computing goes way beyond these statements, and scientific computing involves scientific theories. So thinking Newton's equations of motion, we'll see some more examples today about scientific models, and they're often expressed in high-level math concepts that not always can be computed exactly. Like for example, if pi is included in your scientific model, well, you can't exactly express that in all of its precision, essentially, in a computable model. You have to make some kind of approximation. You have to turn this into some kind of computable model. And the idea is that scientific software implements these computable models as code, and there's still now a mismatch between the code and what reality is, that this is our best understanding of the scientific phenomena, or a model of, that's probably even more precise. This is a model of our understanding of reality, and we want to compare our model to reality. Is it a good model? Is it not a great model? And traditionally, mathematics and scientific theory are established by hand, and then humans manually translate the theory into code as best as they can, hoping to avoid bugs, and then run it, compare to experiment, often identify bugs that way by seeing mistakes or disagreement with experiment or finding things that disagreed with their intuition and so forth. But our goal is to, can we represent all of these things in Lean and represent the math, model, and software in one interrelated and interconnected system? We also talked about lists versus arrays. In Lean, a list is a linked list, and an array is a Python array. A list in, in Python, a list is an array. Lean also has arrays, and we're going to encounter that just a little bit in the differences between these today, and I think that Tomas is going to be covering a lot more about lists and arrays tomorrow as well. A very important idea that we also talked about is polymorphism. And this is when a single symbol represents different types. Polymorphic functions take variables that can be more than one type. And so here are some, if you have a function in Python, a plus b, for example, if you give it things of different types, then you get different answers coming out. You can give it a float, you can give it an integer, you can give it a string, a character, a list, object, and it will do different things. This is sort of, it's referred to as overloaded, essentially. The plus operation does that. And this is, in Python, it's essentially ad hoc, that under the hood, the compiler just looks at the character plus and it figures out from the types around it what kind of function this should be referred to. And so these are technically different functions. But polymorphism in Lean is made possible with generic types. And these get inhabited by specific types based on context. And the important one to talk about this time is we had this example from lecture 8, I believe. Here we were talking about a function definition here. And this is Langmuir, and it's a function of k, eq, and p. And the alpha here is given as a generic type, and this nonetheless allows us to define this function, k eq times p over 1 plus k eq times p. And so we've now defined this function, and we can evaluate it. Langmuir taking in floating point operations. When you provide floating point operations into this type, it will figure out what it is supposed to do based on the operations and the definitions of these binders of multiplication, addition, division, and the number 1, for example. We can also do proofs that if we define all of these arguments as real numbers, well, we can define the Langmuir function right here. And now we are proving that all of these hypotheses imply this function, the very same function that's given up here. So this is essentially, after after 9 lectures, we've kind of established and shown how to bridge this theory and computation gap using polymorphism in Lean that allows us to write proofs about things as well as do calculations. And the final bit of review to bring in is this analogy that David Christensen brings up in his Functional Programming in Lean textbook. And the idea is, how do we conceive of input and output of programs? And you can think of this restaurant where you have the front of house, dining room, and the waiter who communicates from the people in the dining room to the kitchen in the back of the house by passing messages, by passing notes. And in Lean, this analogy relates this real world, if you would, to the input-output monad. And then this inside the kitchen, under the hood of Lean, we have these pure functions, we have mathlib, everything is this verified logical syntax. We can understand and trust and prove and guarantee termination of all these kinds of things. But that is too abstract. It's too disconnected. It's not going to allow us to run the kinds of software that we would be interested in. We like to input things into our software and get outputs and print things. And in order to interface that, we introduced some examples with the I/O monad basic. So this was lecture 9. We talked about how you can take input from standard input, you can write to standard output, and we introduced this CSV reader that allows you to take in a file, for example, and read in the data into that and then do things with the data. And so that takes us to our first application, which is about adsorption. And I'm a chemical engineer. A lot of my PhD and postdoc training was actually studying molecular simulations of adsorption, understanding how molecules move from a gas phase or a liquid phase onto a solid material, and it's the foundation of a whole bunch of different technologies. So if you have a Brita water filter at home or in your fridge or something, there's going to be a solid material in there that picks up molecules from the water phase. So if you would have organic molecules that might lead to some kind of funny flavor in this, and there might be toxic chemicals in there, we'd be concerned about those being in our drinking water. And so if you put a solid porous material, these molecules will go and stick onto that porous material. The second picture is a catalytic converter. And a catalytic converter, now it is principally about doing chemical reactions, turning the soot particles, the smog molecules, and turning those into things that wouldn't be pollutants, for example. But before those chemical reactions can happen, these molecules need to move from the gas phase and stick onto the materials of the catalytic converter. And depending on how you design this material, you get different behavior of this. Picture C is actually of a gas separation unit. This is for taking air and separating into the constituent gases of nitrogen and oxygen. So if your goal is to get pure oxygen, your purpose might be getting medical grade oxygen. If your goal is pure nitrogen, well, then your goal would be liquid nitrogen, maybe for coolant applications. And generally speaking, people will go and collect data. You change your gas pressure, and then you measure the loading. And so as your gas pressure goes up, then you get more molecules sticking onto the gas until eventually the material gets full and it sort of saturates. But depending on the material and molecule combination, you end up with different kinds of curves. And people have come up with these different equations over the years. Some of these are empirical, some are semi-empirical, some are based on derivable mathematical theories. That's especially the Langmuir and the BET models. And so Langmuir is really, really popular, and I was illustrating what that looks like. That's a relatively simple theory, though. This one was developed in 1918. The first one contributed to the Nobel Prize, actually, in chemistry for Langmuir, who developed that. BET is also a really big deal. And so this is called BET because of the last names of the authors of the paper, Brunauer, Emmett, and Teller. And this is, yes, Teller from the Manhattan Project. Just before that was getting going. And they took a sabbatical together and thought about this adsorption problem and came up with this new theory. And it's been really important. It's got more than 36,000 citations. It gets cited a lot because people doing experiments end up invoking this theory on a routine basis. And people have also built on top of this, developed alternative theories that change some of the assumptions in the theory in order to get different kinds of relationships. But the bottom line is you end up with this equation for loading as a function of pressure. And then you have two unknown parameters, this Vm, which corresponds to the volume of one monolayer of molecules on the surface of this. And C describes the interactions strength between molecules on the surface and the molecules on the above layers from this. And the idea is, the general description of the theory is that you can absorb molecules onto the surface, but then once a molecule has absorbed, more molecules can stack on top of each other, up until an infinite number of layers. And when the number of layers becomes infinite, the understanding is, well, that actually is going to be a liquid phase. If you think of the diameter of a molecule, we're talking nanometers, so forth. And so like if you're thinking even a fluid that's 1 millimeter in length, we're talking at, millions of molecules stacked up. Now, they're not going to be stacked up in a very orderly fashion like this in reality. But the idea is, in the limit of an infinite number of layers, we would then just say, this is going to be the liquid phase condition, and the pressure at which that occurs is going to be my saturated vapor pressure. So let's go to that paper, because I really want to take you through a little bit of the story on how we tackled this problem. See, I had first done Langmuir, and I went and looked at the Langmuir paper and read it, essentially, and I could pick out, these are the 5 assumptions. And this would be my conjecture. So I then was able to express that in let me jump to that. Here we go. I was then able to simply, I read the paper, I wrote down these 5 premises, and these are just algebraic equations, and they're actually pretty clear. I mean, just the last one maybe is a bit implied, kind of not exactly explicitly stated in the paper, but we write down these 5 premises and write down our final conclusion, then we can prove that this is going to be the case. But it was harder for BET, and the reason I actually got into Lean in the first place was because I was interested in BET. We would have data sets that it was understood this is described by BET, but how could an AI model that generates a Langmuir can easily prove things, because just doing those algebraic manipulations is easy for an automated solver to handle. But BET is a lot harder. And if you open up the original BET paper, you will see their derivation. And this one is just trickier, because you read this, and the first equation in this section that you see is we have this idea that we shall let S0, S1, S2, and so forth to Si represent the surface area that is covered by only these layers of adsorbed molecules. Since at equilibrium, S0 must remain constant, the rate of condensation is equal to the rate of evaporation from the first layer. So I'm like, okay, I have an equality here. Cool. But what am I supposed to do with all these subscripts? Ooh. Like this is varying, and it's only kind of defining for the very first layer, the way they've written this. They've written a 0 and a 1. Okay. And now it defines things. It's really helpful. I know what the pressure is, the heat of absorption, we have these constants. And then it says, well, now we have this. So this is the second layer. I have another equation. And then I have and then we can simplify this. So I'm like, okay, we have this simplified equation that comes from this, and then we say extending this. So now we have this weird thing, right? One equality dot, dot, dot up to the nth equality, this is really weird looking, right? It's like, how am I going to write this down? This is not an equation exactly. It's a whole scheme of equations. That's tricky. We also have this. This is the surface area. Area is the sum of all of the areas that get contributions from each of these SIs. So just to remind you again, this SI is the surface area that's covered by how many layers of molecules. So yes, this makes a lot of sense. Okay, I understand this one. We start with the surface area with 0 molecules, the surface area with 1 molecule. And so we would have, the surface area from 0 plus the surface area from 1 plus the surface area from 2 and 3, and we need to make this a general way. So I mean, this one is pretty straight. This one is a little easier to understand, but it involves an infinite summation, so that's a little trickier. Lean has infinite geometric series though. We have another relationship. The volume is this. Okay, sounds good. So now we have the volume, and we get this equation. So we are saying, how much molecules per area are we getting? What is the density of, what is the loading on the surface? The molecule per area is given by the ratio of these two infinite summations. And then we can do some math, which again involves, this is an equality equals dot, dot, dot. That's kind of messy, right? That's tricky to say, but we can express this. And then we get into some of the weeds of this, of the derivation. I'm just going to slide through this and jump to another point. Substituting this gives us the following. Okay, and now we have two infinite geometric series as a function of this x, and we can convert the infinite geometric series into an algebraic expression, and that is the most elegant part of the derivation, because now I use one definition here, I use another definition here, and I have this equation. There's no more summations. So this is famous equation 26. Remember that number. We're not there yet because the x isn't meaningful to us yet. X is just a number that represents some of the interactions that were going on that are described in equations 18 to 22 here. So in order to get x into something that means something, there's this idea. To make, here, let me read the text of this. If we deal with adsorption on a free surface, then at the saturation pressure of the gas, an infinite number of layers can build up on the adsorbed surface, adsorbent. So at the saturation pressure, for those not in chemistry, the saturation pressure is going to be the pressure at which a liquid turns into a vapor, or a vapor turns into a gas, into a liquid. For water at 100 degrees Celsius, the saturation pressure is 1 atmosphere, essentially what we feel around us most of the time, okay? And so they're saying to make V equals infinity when P is equal to P0, X must be equal to unity. Thus, from 19, it's saying from 19, these two things follow. We do the substitution, we obtain this isotherm. And that's equation 28, and that was what we formalized. So we did this in our paper. You can read it on Digital Discovery. It's also out on the archive. But bottom line, our lessons learned from all of that, and I'll show you the code in a minute, is it was hard to sort out what are the assumptions from what are the intermediate steps. And how do you state the assumptions? That's just kind of tricky. Are we doing it correctly? You can notice that there's a big gap between the natural language of the scientific theory and, I mean, and the kinds of objects we've been talking about in class: structures, functions, propositions. Those things, it's not exactly obvious how you're going to structure all that together. So you also have some bit of freedom about where you start and where you end the formalization process. There's extra proofs to do. We could say that for P is much, much less than P0, equation 28 reduces to this. Oh, okay, interesting. We didn't do that one. We ran into some issues with that, actually. There's some extra stuff. Instead of doing an infinite summation, we could do a summation of n terms, and we arrive at this. And there's some limiting cases to look at. There's and this is also starting at section 2. If you go to section 1, well, here we have equations. These are equations about dipoles of molecules, equation about the polarizability of a gas molecule, and the ratio of these induced dipoles. And I mean, we studied this for a little bit and ultimately found that it didn't directly help us with that, and we opted to simply start the derivation here in section 2. And so when that's another thing to be thinking about, because a lot of the time, I mean, and it's definitely the case in this paper, is, let me go to this start of section 1. This is talking about the polarization theory of de Boer and Zwicker, and they're just thinking about the interactions that molecules have. And the layers of these, equilibrium, pressure, Boltzmann, there are these theories, and there's a little bit of derivation going on here, but it doesn't exactly connect to what we were doing before. And we opted to start in the middle, essentially, if you would. We started with if we as the scientists judge the second section of this to be a more critical part of the work. And you'll find that in classes too, like you find class notes from different professors. They usually start the derivation maybe with a qualitative description of section 1, but then a quantitative description of section 2. So that's a point to be made about this, is you have some bit of freedom for this. And we proved equation 26 and 28 followed from the premises that we defined. And you can find that code on here. And in the coming days, we will have this without bugs. But we had the proof a while ago. We wanted this to all be consistent with the latest version of Lean. Let me get my info view out. Where's my info view? Oh, here it is. No, it's not. Lean info view. Nope. There we go. Great. Oh, wait, we did get it cleaned up. Cool. Okay. So here is our code. And we started with a structure. So we've seen structures before. In this case, our structure defines the key variables as real numbers and also defines these inequalities. So this carries these propositions that we'll be using over and over again. We could have potentially put these, well, and then we have these definitions. And we're using first layer adsorption rate to refer to the C1 times P. Two real numbers that are, we have the C1 is a variable in our structure, and then P is just a variable inside this function. So this is a function of P, and it takes in the whole BET system. Because we're taking the whole structure, BET system, into this function, that's how we have access to C1. And when other things, it's important, when other kinds of functions take in this structure and they refer to C1, they're referring to the same kind of thing. We also then have an nth layer adsorption rate, We have this definition of the adsorption constant, which here we just define as y over x. We're following the text from the paper. Then we have this sequence. This is a recursive function. We take in the BET system, we take in the pressure, and we have a function that outputs a natural number to a real number. And if it is 0, we return the surface area of the 0th layer with 0 molecules adsorbed. And if it is n, then we return this Matthew function, which we get from one of the equations of the paper. And to decide that this is going to be the sequence that we started with, as opposed to any of those other things, it took some thinking careful about what we were doing. We then have the volume adsorbed. And so the volume adsorbed is this V0 times the infinite sum. And we have the surface area, which is the infinite sum of this. Oh, okay, and both of these take in the sequence of this. So we're taking in this recursive function that maps from state to real number, and we're doing a summation over all of those states n. So we return a real number after all of this. And that's given a simple notation. So you'll notice we're using local notation. That's a nice way to invoke a, the capital V here is always going to refer to BET.volume adsorbed. And now we can use V and it means that, and we don't need to write out the whole thing each time. So these are, if I can get them all on one screen, these are the 1, 2, 3, 4, 5, 6 premises that define our theory, and then we have our conclusions. And we want to prove that this function follows, and if you look at all of the terms, this should be matching up with equation 28 and with equation 26, with respectively. So we can just name these Brunauer 28, Brunauer 26, according to the numerical parts there. Oh, we have a comment. I can't see where this function calls itself. That's a good point, actually. It takes an S as the BET system, and in the recursive call, we invoke S. Okay. Oh, no, we would need sequence actually here. So I guess, no, this isn't recursive. This is a inductive. It's an inductive type. Don't hold me to the terms I'm describing. We're using succession. The next thing, it's a sequence object. And fundamentally, yeah, true. It wouldn't be a recursive function that calls itself, but when you do pass, yep, it is induction. It's in, Colin is clarifying. I think it's induction, yep. So when you give it a thing, okay, it's going to do a match statement. And it's going to match the thing it gets to either 0 or to the inductive function call. And yeah, it's defined using induction. We didn't dig into that in this course too much, but if you want to learn more about induction, it may be relevant to what you're doing. The natural number game is a great resource for learning about induction. There's also sections on it in mechanics of proof as well as mathematics and Lean to do induction. Most of the, I don't know. I think induction actually doesn't show up in science and engineering so often, but it did show up in this example. But it's actually doing proofs with induction that allows Lean to prove those things like the infinite geometric series. And we decided the core of this is going to be sequence math. You can also then see we have Brunauer 26 as a theorem. and it invokes sequence math, and then we have some tends to math. So we definitely skipped limits and filters, but if you end up needing to do proofs about actual limits and filters, then go and study those things. We were using that because we needed to use this approaches infinity, essentially. So we have this question of tends to at top, and at top means at the infinite thing. And then we have, there's a lot of steps here. Um, and that's right. And so stay tuned. We had all of these proofs working, but that was a version of Lean and MathLib that was current about a year ago. And we had ported that over to Lean 4 or so. And then Colin was just over the last day trying to clean that up, but keep an eye out on the repo, and we should have the full proof finished cleaning up here as well. But if we go to our paper, you can get a general idea of the proofs that were involved. And so the code in this paper again is Lean 3. Don't worry about that. Just look at our repo, LeanBET, to get the Lean 4 versions of this. But bottom line, we decided that this equation was the linchpin to it all. And so we proved this using different lemmas for these infinite geometric series, which were in MathLib. And then we need to do sequence math in order to change this into this. And once we can do the main math goal here, then we can close it out and prove Brunauer 26. And the last part was unexpected. We were then trying to derive 28 from this paper using these equations about this. And our comment about this is another lesson we learned about formalization, okay? We ended up stating that this equation follows from an assumption that 1 over CL is equal to P 0. That's not how they did it in their paper. In their paper, they said, let me take, down here, let me take the limit as my loading goes to infinity, and then at that condition I set P is equal to P0, and then I find that my CL should be equal to 1 over P0. And we had to go in the other direction. We had to assume this and then show that the other stuff followed. And to us, that really illustrated the rigor of Lean, that when we were talking about these limits and the logic of, do you take the limit first and then make an equality assignment, or do you make the equality assignment and then from that show that the limit is equal to this? We were found that this version was a lot easier, and in fact, part of the problem was because this mathematical function has multiple divide by 0 cases, essentially. So mainly the focus is on when P is equal to P0, that I get a division by zero, but there are other ways from this other term that can get this division by zero. So I can't just say, if my loading goes to infinity, then I'm going to use that condition, because it actually goes to infinity in multiple ways. And instead, it's crafted in a different sort of way. And so Lean helped us catch those things, essentially, helped us make the derivation more rigorous. Okay. So that's just to sort of summarize how we can do some fancy proofs. And that's the most elaborate derivation that we've formalized so far. You can see there's tons of lines of code in that. It could be broken up into intermediate lemmas and so forth. We've generally found that doing proofs about these kinds of messy objects is inconvenient and lean. And I would say a wish list would be some tactics that can do algebraic simplification on non-trivially, on long and medium length algebraic expressions with one or more division operations, because it tends to take a lot of steps for us to unpack all of the order of operations here, do these rearrangements and things like that. Not typically how humans think of this. I would say, and I can now simplify this into that. And if more powerful tactics were able to close those goals faster, that would be appreciated. Okay. So the next part of this is code, executable code. And the motivation for this comes from this really neat paper that studied BET absorption analysis, and they sent the same data sets to a whole bunch of different labs. And each lab did BET analysis on that data set. The goal is to get this VM parameter. What is VM? What is C? And they compared here just what is the value of VM. And all these different labs, they got the same XY data, but they got different answers for this. And this is all over the place. The Python code. So essentially, they do all this work to get to the bottom of where do these discrepancies come from? How can we do this in a more standardized way? And they put forth this Python program, BET structural. Oh, I forget what the SI refers to. But Betsy, basically, and this is their paper. And to illustrate the crux of where different answers come from is to illustrate the workflow of applying the algorithm. Here, let me actually go on to the next slide real quick. So BET analysis involves taking in your XY data. You filter this data to focus on this BET regime. Then you linearize it so you can do linear regression, get a slope and an intercept, and then get fitted coefficients out of that. I glossed over this point. If you rearrange, so this one is the linearized form. So VM and C are your unknown constants. So this would be the intercept. This would be the slope. And you just need to rearrange your P over P naught and Q as these functions in order to get a linear equation where you can optimize these coefficients and get your values out. Then, okay, so how does their method work and what's the problem? So the problem is, in practice, you go and you get experimental data, but not all of that data is understood to be relevant to the BET model. The BET model brings in all sorts of assumptions about molecules interacting with the surface, stacking on multiple layers. And if you decide that I'm going to discard all of these gray points, then I have the red points remaining. And the red points are going to be what form my data set for doing linear regression. How do I decide what points are going to be red and what are gray? How do I decide which points to include? Well, the question is they need to satisfy these so-called Roquerol criteria, which were proposed by an expert in absorption who said, you don't have good data if your data don't satisfy these things. And some of these are pretty obvious, like the C constant must be positive because that has some physical understanding of what the C constant in your equation should be. This must be monotonically increasing. If your pressure increases and the number of molecules you have loading is decreasing, that is thermodynamically inconsistent. That doesn't work. You also have these other conditions. And so the idea is you have your data points 1 to n, and if you include different windows, different sliding windows of this, you will get different BET areas. You will check whether these settings lead to consistent or inconsistent results with the Roquerol criteria. And then among those that are consistent, you pick the one that has the lowest error. And their code, their open source Python code implements this method. It gives you the results. It gives you all these other kinds of things to look at. And our task was, let's implement this calculation scheme in Lean. And so as a high level, our goal is to implement this calculation procedure, but also have proofs about it. And then draw lines connecting the proofs that we're writing to the different objects in our code. And use polymorphic functions so we can be executing our math with floating point numbers, and we can be proving our things with real numbers. And so we are still working on this. In particular, we're working on implementing the Roquerol criteria and getting this filter to work, because it essentially involves, if you have 30 data points, you will be, if you're going to do every possible window in that range, you're doing 28 times 29 sets of data, essentially. That will be passing into that. That ends up being a lot fewer because the minimum window size is 10. But that means you need to have some loops. You run this over, and each time you're checking if this is working in the BET regime. What we have now is the linearization and the linear regression running in Lean, along with proofs about these things and some results that show our code. If we give it the pre-filtered data set, okay, so I have the caveat here, filtering is being applied in Betsy. We get what Betsy said it should do for the filter, and we get the same answer. So, but a point, this comes back to test-driven development. This is not, this plot is not what we're aiming for. We're not trying to, first and foremost, obtain a numerical match to the standard. We are trying to define the mathematics and have proofs that our code is correct. And in a sense, the Lean number will be the number that we believe first. And if Betsy agrees or disagrees with Lean, then Betsy is out of place. Now, there's some caveats on how you should be thinking about this, because you come back to these. Oh, did I lose the Roquerol criteria? I guess I lost that. Okay. It comes back to these Roquerol criteria being, these aren't necessarily the be-all, end-all correct way to implement these, but it is the way they implemented them, and so we are following that. So semantically, we aim to line up with them. And we do look at comparison of our answers as being a way to check the semantics. Are our semantics matching their semantics? If that makes sense. Okay, so let's get into the code. One more thing though. First, a high level look right here. Okay. So we're going to walk through a few files. And so no guarantees at all about future code versions. In fact, just working through this the last couple days, we already know some different ways we would organize the code than is shown right here, but this is how it's working right now. And you run this high-level BET CSV examples file. This is then going to import stream read and start a cascade of functions. And stream read calls CSV LRM model. BET CSV calls this and invokes stream read, which calls main. Main is called, just like we were seeing when we were learning about I/O and function execution. We then have main calls process. Process calls dump. Dump calls parse. Parse gets recursively applied until the CSV buffer is empty, which calls linear regression process, which starts doing the math. Then we do the math to do the linear regression, and then we return the output. And the idea here, and this is this functional programming style, is all of these functions are linked together front and back, front and back, front and back, front and back, so that linear regression returns LRM out, which passes this all the way up until it gets to the final code at the very top. So dump receives, okay, the stuff that is connected all the way down into the math and all that stuff. So let's walk through the code. I'll also say I'm not beholden to the file structure. I would probably put all the proofs maybe in one folder, and then we could have all the executable code in another folder. But that's getting ahead of myself. So we start with this file, and it's a little tricky, and this is the main part I would reorganize, is because I would actually say we should put our main function in this file, and then our main function or maybe not. It depends on exactly how we're doing with this. Oh, I need to restart the file. Okay. And so we provide paths to some different CSV files. And this is importing the stream read at the very top. And stream read is where we have main defined at the end. What does main do? Well, main calls process. What does process do? Process, after you dig through the I/O complications, okay, process calls dump. And dump is right here. Dump is going to read the text buffer that's coming in. If the buffer is empty, we will call LRM process. The buffer is not empty. Instead, it has something, so we will call parse. And parse gets called and is going to parse out the first element in the array. We then pull the rest of the array out and apply dump again to the output array. And so this is a recursive function call, and it will run and run and run until our buffer is empty. And once our buffer is empty, now we've gotten to the end of reading our file. Now it's time to do math on it. And now we have this output array, which has things in it, and we will be passing those into LR process. What is LR process? LR process is a polymorphic function. You can see all of these binders. Okay, this one is also written with do notation, so it has a imperative style. And we do things like check X unique, check Y unique. Because if I have, I might have 10 different data points in my linear regression, but if 10 of them are all unique, okay, then I have an ill-posed problem, and I can't do linear regression on this. I can also check if they have mismatched lengths. I can't have X with 20 data points and Y with 19. That's ill-posed, so we get errors out, passed out, if we have data sets of an incorrect size. What is it calling in here? It is here it is. It calls linreg. And so the linreg is up here. And this is our math. And so now this is, again, this one is following a we do sum of x squared. We do sum of the y's, sum of the y squares, and so forth. If you're familiar with the math of linear regression, then this should look familiar, but we're just calculating all of these terms and then use all of that to back out, well, what would the slope and the intercept be out of these things? And importantly, it produces an output. LRM out will store the slope. It's a structure that stores the slope, the intercept, the Pearson's R coefficient, and the mean squared error. LRM out, we have our result. We made it. So essentially this comes back to, then it passes its way all the way back through. linreg returns LRM out. LR process was trying to call linreg and now has a result. It has LRM out. So LR process takes it. LR process, it works all the way up to the top. And the result is here we go. We get our slope, our intercept, our R value, mean squared error, coming out for the first one. The second one, we get an error. X and Y have mismatched lengths. One array is longer than the other. Okay. The difference between these two CSV files, you can see. This one is 2 rows with a whole bunch of columns. This one is 2 columns with a whole bunch of rows, but also a third column. Wait, did I do that right? No, I guess just 2 columns. Yep, okay. So this one is a different style, a different format compared to the other one, and we built it for the other format. I think where we're getting started, it was easier to do it that way. We have plans to refactor the CSV reading and data handling so that we can take in data of this form too. Okay, and let me close this. Here we go. And we get slope intercept R value, mean squared error for all of these things too. So there it is. That is this connection. And do we have the BET infinite connected to these things? I don't quite recall. But the point being you could just define all of this, and then you could write a theorem saying Brunauer 28 corresponds to the equation that we're starting from in the math that we're looking at. And if you can write a proof connecting these things, and you've integrated the compute, and you've integrated the proofs. Any questions? Any thoughts about BET analysis in Lean? And Colin added some things. There was a MATLAB update that changed some syntax for lemmas causing irregularities and some steps in field simp. So every once in a while, MATLAB update, it breaks old things. We will have that tidied up. So Urja is asking, how do we create the columns and rows? Oh, good question. I think I glossed over that. So the parse is from CSV cat, which is a CSV reader. If you're asking how did I create the original columns and rows, well, I just started with this data. We started with the CSV file, but then CSV cat, as we saw before, this one has a parser. Oh, I don't want that over here. I want it here. There we go. So parse takes in a string and it produces an array coming out. And it gets called when dump is in process. Dump isn't about creating columns and rows. Dump is just about reading in the IO stream and producing an output array. How will it get an array out of this? It needs to apply parse. And there's parse result, and there's also, I think that's it. Yep, so there's parse result. Oh, and there's also parse. We needed this string from UTF-8. That's in Lean Core. It allows you to turn a byte array string into a byte array into a string. And then after that, we turn the string into floats. All right. Okay. Now we're getting to LeanMD. Let's talk about molecular simulations. Well, again, we're going to start with some background of this and then get into molecular simulations. If you have access to the slides, you can find this on slide 29. There's a nice little link. You can play with molecular dynamics simulations in your web browser. The reason we do molecular simulations is because these are basically understood to be a computational experiment conducted on a molecular model. And this is a picture, it's a figure from an old book, Computer Simulations of Liquids. This has been around since the Not this millennium, for sure. And this one, there's a there's some correspondence between the syntax semantics figure that I was showing. We have reality. Okay, I can do an experiment with reality, and I can get my experimental results from this. I can also propose some kind of model system that maps imperfectly to the real systems. And if it's going to be an approximate theory, then I can make a theoretical prediction. I can predict, I'll do analytical transformations of my theories, and then I will say, this is what my theory generally predicts. Alternatively, I can get computer simulations, and the difference between these is computer simulations have to be computable and often invoke numerical approximations and things like that, and we get simulation results. And all of these together allow us to both test the model as well as to test the theory. So if my simulation agrees with my theoretical prediction in a case where I have an analytical solution, then my implementation of my computer simulations are going to be valid, and I could maybe trust them when I move to something where it's not possible for me to get a theoretical prediction of this. If I'm curious about how my theories are correct, well, I can compare them to experiment, but often the real world systems that I need to simulate, I need to look at are so complex that I can't actually use approximate theories to get the salient information out. I need to do a computer simulation. Molecular simulations in particular are really the only way to get the thermophysical properties of a molecular model system. We can get thermophysical properties of experimental systems, real systems, but we can't use experiments to get the thermophysical properties of a molecular model system. And we can see things on the molecular scale. We can simulate what these are doing, and this is often really helpful. Sometimes people do high throughput experiments high throughput simulations in the computer in order to screen out things that would be difficult to look at experimentally. And the three main components of molecular simulations, we define the model, and this is either going to be using like quantum mechanics or these classical force fields. We'll talk about those more in the next slide. Then we compute where the particles move, and we simulate the different configurations that these systems can take, and we analyze the statistics that come out of these ensembles of configurations and estimate thermodynamic properties from those. So we are mostly focusing on force field today. If you're interested in quantum mechanics, okay, the math involved in quantum mechanics, I fully support someone going off into a big, bold goal of formalizing quantum mechanics in Lean. I think that would be a project some people could take on. That's not our specialty, though we are tied to those and use those things. We're more connected onto the force field, the molecular simulation side of things, where we simply use simple equations to model the interactions. And the idea is you have interactions within a molecule. These are called bonded interactions, where we just use these little equations to describe how bonds stretch, angles stretch and dihedrals twist, angles bend and dihedrals twist. We have non-bonded interactions. So these are between different kinds of molecules. And these typically fall into two categories. And the examples I'm showing you here, these are by far the most popular models, but they're certainly not the most accurate or always the best choice for a given system. It is, however, the ones that have been around the longest and the ones that are computationally cheap enough to address pretty lots and lots of diverse behavior. So the next question is, how do we get configurations? And there's two different simulation types. We are focusing on molecular dynamics. And the idea is you get one single system and you run it for a long time. The average quantity of this is going to be averaging out, for example, the density or the energy or the pressure of this system over a long time interval. And you measure that property at all of these times, and you can take the average of this. Monte Carlo is a different perspective on this. Here, there's an ensemble average that comes from averaging this using the probability distribution function of the systems as the measure of this. And we integrate over all of the positions and momenta of the particles in the simulation box as a function of the probability of that they're in these positions and the property that it has at those conditions. This is an integral, that we can't solve analytically in the vast majority of cases, so people use Markov chain Monte Carlo to solve those. And I've done a lot of research in that area. That's going to be more difficult to bring into Lean than the molecular dynamics approach. So we're focusing for now on molecular dynamics. But so this is a short scheme of how molecular dynamics software works. We start with xi. These are all of the initial positions of my system. So you can look at this picture, you can say I have 7 molecules here with 3 atoms each, so that's 21 different particle positions. I calculate the energy that's related to these, and we would use those equations I was showing you before. These equations, if I jump back to it, these equations are functions of distance, you can see. So we have distance, this position vector. We have the bond length between the oxygen and the hydrogen. We would have the angle between the hydrogen, oxygen, and hydrogen. And we can do the derivative of the energy with respect to position to get the force, and divide the force by the mass of each particle to get the acceleration. And now we have, where are these things moving? So we initialize with a set of positions. We initialize with a random velocity distribution chosen from the Boltzmann distribution of velocities. And then we say, well, what are my new positions? My new positions are, let's go forward in time according to some small step A, and let's go forward in time for my position. And we numerically integrate the Newton's equations of motion. Definitely check out Silene. Tomas has been figuring out how to do these kinds of numerical integration things in Lean. We're not quite there. But the bottom line is you go and you do this, and now this is showing the changes across these things. So like if the forces are applied in this direction, then you move all of the particles in those directions, and you end up with a new position for each of these molecules. And that's one step. Then you run them again and again and again and again, and at every single time step, this property might be the energy of your system. So it's going up, and it's going down, it's going up, it's going down, and so forth. You take the average of all of that if you run the simulation long enough, and you will get useful information about the system. So a brief thing, just so you can see. So Monte Carlo is you do generate new configurations, but you follow a completely different approach. You will randomly perturb the system. So I'm going to randomly pick a molecule, randomly move it into here, and then I look at just, was the change in my energy favorable or unfavorable, and we use some math to accept or reject it. Monte Carlo is really helpful when you're dealing with different kinds of ensembles. So An ensemble defines the kind of constraints around my system. So one ensemble might be saying constant number of molecules as well as constant pressure and constant temperature. Or I might say constant number of molecules and constant volume and temperature, or constant energy, constant number of volume, constant number of molecules, constant volume. These are different kinds of systems, and they represent different scenarios in the real world. And the neat things about Monte Carlo is it can access some more exotic ensembles than molecular dynamics can, but we can talk about that another time. The other thing, I have one slide. These are from my lecture notes, or these are from Samiha Sharlin's lecture notes that she taught in my graduate thermodynamics class. And I point to some of this stuff. This comes from statistical mechanics. This is the partition function. We have n factorial, these n-dimensional integrals over stuff. So this is really abstract, advanced kinds of math, and Lean can express all of these things. It takes some work. It takes some, MATLAB doesn't necessarily have all of these things ready to go. Sometimes it has more generalized forms of the operations that we need, and one would need to make a more specified version of that to apply it in these contexts. But you can see these things are like thus. The word thus implies proof. So we can take the math of statistical mechanics and we can start writing proofs about it. And finally, this is what these kinds of things can look like. So you can see different molecules filling up these simulation boxes and so on. So our goal, and finally, molecular simulation is actually like a really big deal. So most of our supercomputers, until like the very, very recent ones, well, even the very recent ones, most of the supercomputers for science built by the United States have been designed for physics-based simulations, and molecule-based simulations are very often a big part of those. People use them to study all sorts of practical applications, from gas separation to biomolecular systems to physical chemistry. And just in a 10-year period, over 100,000 papers were published. And there's a large number of people working in this field, a lot across many different disciplines, both in engineering, in chemical engineering, as well as in chemistry, molecular biology, things like that. So here's another way to represent the ingredients of this. You need to define a simulation box. You need to populate it with particles. You need to calculate the energies among the interactions and get their forces, and then move them by Newton's equations of motion. And we are working on this. But essentially, for now, we are focusing on this energy calculation. This is the very first step. So we're just getting into this overall process, but we are developing code. We are validating it. We are making sure it works. And the general flow is we apply periodic boundaries. We apply minimum image distance. We calculate the Lennard-Jones potential, get the total energy of this system, and we can have theorems, and we can have proofs about these functions. And that's something you can't do in any other code, which is really neat. In our case, we're also testing this against a standard. The National Institute of Standards and Technology has a NIST standard reference simulation website that has systems defined and the answers that that system should provide. We have some bigger vision for this. Here, let me walk you through this slide now. So at the core, we have the symbolic formulas. This describes classical mechanics. This describes the forces, the force fields. This defines the constraints around the boxes. And if we turn these into executable code, we need to turn these into executable code in order to get simulation results out of them. What kinds of specifications can we write about molecular dynamics? we can introduce these kinds of things. We can say something simple like a force should be a gradient of the energy. So if I have a function force and a function energy, I should have a proof that they're related in a certain way. We have some more complicated ones. Ewald summation is used to tackle partial charge interactions, and that one's pretty fascinating because it involves summations. And if we can prove convergence of that, that'd be really neat. These kinds of proofs would be formal proofs that the math is valid. We have even higher level stuff where we formalize statistical mechanics itself. We go back to the textbooks, and could I prove that NBMD is modeling the NVE ensemble? This abstract kind of math object here? Maybe so, someday. You know, we're quite a ways from that. May need to get some serious math help with that, but yeah, interested in trying to see what that might look like. And then we have execution specifications. So I might say I have Newton's equations of motion described, but I don't do that. So here I have the calculus-based equation here for my force, but I have a algebraic-based equation for my numerical integration. This is, in order to connect these dots, we have to do a Taylor series approximation, some algebra, some cancellation of terms. We can calculate the error bounds on this. You know, in what cases will the error of my energy, will it diverge and blow up because I'm doing a not great simulation or I'm picking the wrong setup for this, or will it on average stay near zero if I do this? Will it cancel itself out if I overestimate sometimes and underestimate other times? Those are things that we could potentially build proofs for. We have even more mathy things like, you know, does the fast Fourier transform do this? Is an algorithm applying constraints actually going to be provable to rigorously apply those constraints and so forth? And, you know, once we have these, we have formal proofs that the execution is valid. And we talked about compiling Lean into C. We can then finally do that and explore how efficient we can make our code and how it can compete against other things. Okay. Time to go to the LeanMD code. All right, and I'm going to, oh, I have a lot of folders open. I'm going to try to put these in here. Okay. Right before class, I was having some issues getting LeanMD here, so I'm just going to drop them in the BET folder and hope they work. All right. Okay. Nope. Restart file. Oh, I need LeanMD in the search path. Okay. There we go. Uh, well, Nope, I just can't drop it. Oh, I need the Olean. Might just be breaking my VET thing, but it will be worth it if we can get it for the lecture. Just to see. Okay, let's try. Oh, maybe I do. Okay, let me get the lean lake file. Ooh, yeah, if I have, oh, do I not have the lake file? Oh, I don't have the lake file locally. Uh, oh, I have the lake manifest, but Oscar didn't upload the lake file. Okay, we'll open it from the browser and we'll just walk through it without getting type information. Okay, we'll get this cleaned up soon. We were just trying to get this together right beforehand. Okay. Oh no, this is here. Um, the late file.lean is, well, no, yeah, I had lake file.lean in LeanMD. Are you working? No, this isn't working either. Um, all right. Well, I don't want to crunch through all this stuff. I failed to quite get it on here first place. So the main part of this, okay, and bottom line, we are only doing, oh wait, this is for parsing the code. Yes, this is all data parsing and sorting out the CSV parser. We need, here we go. I'll just move it over to here, even though this isn't quite going yet. Okay. Okay, so this is, so up above all of this is CSV parsing, which was the thing we were trying to get in because we sort of in principle have it ready, but um, the, yeah, the CSV parser wasn't producing it to use in the same way that we wanted it to in here. And the logic of this, if I go back to the graph, oops, wrong one. We closed it. Is LeanMD. Okay, here we go. We take in the positions of all the particles. We apply periodic boundaries to wrap them around. And so what this means is if we have a box volume, X, Y, and Z, and if particles are outside of that box, then we wrap them to be inside of this box. Then we apply the minimum image distance. So we don't, the distance of interaction is between the molecule and its nearest image of it. And I guess I need to get a picture of that too. Which I have here. All right. So if I have a box with two particles, they're given in black. If at time 0, they're here, and then time 1, they move to their new positions, okay? What periodic boundaries do is they always wrap them back inside of this main box. So particles never escape, essentially. It's kind of like if you remember those old Mario games, if you run off the left side of the screen, you'll appear on the right side. The minimum image distance says what is the interaction energy between these two particles. If I'm looking at the two black ones, well, I would say, well, this particle could interact with this other particle or any of its images. Is this one, this one, this one, anything in the upper right of one of these boxes is a candidate for that distance. And in this case, this would be the closest one. However, after it moves here, it's not necessarily going to be the distance between this particle here and this one. It might actually instead have this distance be the minimum image distance between the two. And we need to return that distance each time. After we have this distance, we calculate the energy from the Lennard-Jones potential. Then we total up the energy for all of the particles of the system in the box and compare our results against a NIST standard. And so we have things like apply periodic boundaries. And this is going to take a list of floating point numbers, and it's going to take, it's going to take a list of particle positions. It's going to take a list of cell lengths, and it's going to take a list of floating points. And it's going to produce that. So it's going to take in our positions, and it's going to produce a new set of positions. And this involves doing a rounding off of your function. Then we can do the minimum image distance. So the minimum image distance takes in the position, the vector. This is a list of two particles, the distance vector. It gives you the cell length, and it will return what is the minimum image distance. We're following equations that you can find in textbooks about these things. In our case, we had a little trouble grabbing the Euclidean distance type out of MATLAB, and so we defined our own vector norm in order to add up and get the distance of particles between XYZ coordinates. And then we get our Lennard-Jones potential. The way the Lennard-Jones potential works is we have 4 times the energy constant epsilon times an r to the 12th term and an r to the 6th term. Those are defined here as a function of sigma, which is the molecule radius, and r, which is the distance between the two particles. Here we are just following what we need for NIST, where we set epsilon and sigma equal to 1. But this function, in the more general case, would take the epsilon and the sigma as arguments for it and produce those. And if the distance is smaller than some cutoff radius, then we do this calculation. Otherwise, we return 0. And so for all particles that are outside of this cutoff radius, then we get a 0 interaction. The energy calculation was tricky because it involves a sum over pairs. So I need to take in the positions of my particles, and I need to somehow get an energy out of all of this. And so my energy is going to come out as a float. And the way we did this is we made this a recursive function that took in the accumulated energy. The accumulated energy is going to start out as 0, and then it's going to accumulate. We have if statements looping through particle I and particle j. So we do a sum over pairs of all the particles in the system, and we invoke the distance to get the calculation. We invoke the PBC. We invoke the minimum image distance. We invoke the Lennard-Jones potential with the distance and the cutoff, and then we ultimately return energy. So it's a recursive function call where we return energy itself, but now we are then accumulating an energy contribution from one of the pairs, and I, j minus 1, okay, ultimately passes through here. You'll notice we're not using a partial definition, we're using a pure function, because the way we set this up with these if-else statements and the counters I and j, it was able to figure out that this satisfies structural recursion, and we're good. So finally, we then compute the energy. And the energy computation happens by passing in the positions, the cell length, the cutoff, and the system of these things, and then we get our energy coming out. So we can use this. And here is the big example where we have, or maybe not, no, this is a small example where we have 30 particles. And is it going to work? Okay, it does work. Cool. So I guess my lean setup ended up converging all on its own, which is great because you get to see the numbers. So here we get an answer back. This is doing an eval on this set of particles. And so we were doing initial testing by simply pasting the CSV file into Lean as a list of lists of type list, list, float. Still working on getting this all compatible with the CSV reader. Thought we might get that ready in time for today, but we weren't quite there. This code for the largest system that we tested, which is 800 particles, takes about a minute to execute. So it's actually really, really slow compared to most MD codes. If you have an optimized one, this would be taking much, much less than a second to do a similar energy calculation. But part of the reasons for that come back to the difference between linked lists and arrays. Arrays are a lot more efficient. We were working on our math using list and recursive function calls in this, which is going to be something we'll be exploring and testing as we evaluate efficiency of different approaches and provability of different approaches in the future. There's also algorithmic things that we don't include. So we don't yet have things like neighbor lists, for example, and there's other ways to algorithmically change the way you do the coding in a way that will make it go faster. And so if we can ultimately target to pull this into an order of magnitude or so of fast C code, that would be pretty wonderful. But we will see what we can do with that. And so that takes us to the very last topic is, what are you going to build? What will you do next? So Scilab is what we imagine as some database of formally verified science, and don't necessarily need to have all of this under one roof. Currently, we have lean chemical physics, which is nothing super organized. It's mostly introducing this tool to the chemistry community. Joseph Tooby Smith is doing a high energy physics library of formally verified math and lean. We also envision statistical mechanics, molecular mechanics. People, we've been working on thermodynamics. If anyone wanted to formalize quantum mechanics and density functional theory, for example, Hartree-Fock, that would be a really cool approach to go into with this. Fluid mechanics too. This is something that I know Tomas Scriven is quite interested in working toward. There's also more meta type stuff, like what do we need to do to get this stuff right? Having dimensional analysis and handling of units in physical sciences would be broadly useful for Scilab. We also have need for more computer algebra system-like functionality. Can I ask you to calculate something for me? Can I ask you to solve for X or Y or something like that? And last week, I challenged you to start a conversation on Zulip. And these were some of the ideas that people were sharing. Can we formalize probability theory? And thinking on a math lib type perspective of we have probability theory that's missing. I find that interesting and useful. Okay, so could we add that? Things around machine learning, like reinforcement learning approaches with idealized reinforcement learning agents. I shared that we're interested in Markov chain Monte Carlo. We're obviously doing a lot to build in molecular dynamics. One person was saying there's a textbook on statistics, and it would be really neat to turn a statistics and probability textbook into a textbook with lean examples. And I think that would be neat as well for teaching those things. And I thought the most interesting idea was an open-ended question of how could we do data science stuff in lean? And after reflecting that over the weekend, I suggested, how about a pandas data frame? That's a Python library that is very popular. You can import data very easily. You can manipulate it, do things like sorting, filtering, selecting different columns of data to do different kinds of analyses with. And I don't think there's something like that in Lean. We have lists and arrays, but we don't necessarily have a data frame type object, which would be a kind of structure or type to propose to build that would then be organized. So you would have column headers that have names, and you can then have columns and do different operations to data frames, extract information from them, and so forth. So the code that we do for implementing linear regression is really only for problems of y is equal to mx plus b. It's very elementary. The most forms of linear regression that mathematicians understand would involve the multiple linear regression case, where you have many, many x's that are linearly proportional to y. And the generalization of that, I think, would be far more elegant than what we're doing in BET. If someone wanted to formalize that, we would definitely adopt what you're doing there. Until then, we have our one-dimensional case of linear regression. And another thing I think is when you do calculations, we often get results and we want to see what those results look like. I don't really think that doing visualization in Lean is really going to be worth it unless there is someone with a passion for that thing. I'm not sure about the capabilities. I'm seeing Simon is suggesting there's proof widgets, which is exciting for visualization and proof tooling and tactics. So, by all means, like if there'd be ways to make a plot of XY data and draw lines through it and have symbols and those things, then go for it and explore that. But I think also just from my perspective, if we could just connect this, build some kind of pipeline, some way to streamline this. If you have Python and Lean installed, then you could run Lean, get numbers out, and then pipe that over to Python. So Python reads an output CSV file that Lean would print, and then you could visualize it in Python, and then you would have access to all of those rich tools that people would build there. But that obviously involves all these extra steps and extra installation challenges. If it could all be done within Lean, so you can pop up in your info view and there's your plot, I think that would be really cool. Ooh, Julia? Sure. Julia would certainly be more efficient than things. I think when it comes to data visualization, efficiency isn't such a big deal, but Julia is a popular language and it has mathematical expressivity, I think, that's particularly valuable when it comes to defining high-level operations. I think there will be a lot of cool Julia Lean interoperation that people could work on as well. But again, if you move past, if you start dealing with multiple languages at once, that does increase the learning curve for it. Urja is asking, how do you generate random numbers in Lean? I don't know. I wrote a proposal with Jeremy Avogad on proposing to research this thing, essentially. And we had some ideas there, but need to, yes, exactly, build in monads. It's stuff that goes above my head. I know what we would like to use it for, because I think when it comes to writing proofs and proving that your code is correct, that's the realm of random numbers is really where this stuff can shine, because it's one thing to say, I've written molecular dynamics code and I'm proving that it's correct. But the thing is, you can run molecular dynamics code the same over and over again, and you always get the same answer. It's deterministic. But and so goes with a lot of the kinds of calculations we do. But there's probabilistic programming is intrinsically random. And this is where debugging code is really tough. One of my colleagues at NIST, he maintains this library of Monte Carlo software that anybody can use. And he has these continuous integration, automated testing, and so forth whenever he updates the code. And sometimes these tests flag false positives, that it says there's an error, okay, but there's no error. This didn't actually have any problem. It's just because you're running the test, and this time the random numbers that it happened to call ended up triggering this error message. And maybe if it's a 95% confidence interval, you can imagine this triggers about 1 in every 20 times. And so that means you're wasting your time debugging. Or I've had cases with software that I was working with where it wasn't until someone decided to run the code for a really, really, really long time to narrow down the confidence intervals to be tiny, 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 and narrow, and then to realize that, what should be equivalent, exactly identical scenarios is giving us a different answer. So now there's a bug somewhere. We found it. Nobody ended up running this code that long before, okay, but we found a bug. We found an error, and we only can see that in expectation. So if that's something you're interested in, yeah, definitely ask more about it on Zulip. People have ideas about connecting this to the Jiri monad, for example. I bet it's going to involve measure theory to some extent, because that's how probability and statistics are grounded in the axioms of mathematics in Lean. But it goes beyond my immediate expertise. But if people do start digging into that, we will eventually learn that and teach it at some point, because I think it's really important. It's the use case, I might call it the killer app, if you would, of Lean to make, if you can prove that probabilistic programs would be correct and also implement them rigorously, then there's tons of applications from um, machine learning things to finance to probabilistic simulations of phenomena in chemistry and physics, biology. Yeah. Ooh, Alistair is saying I'd like to calculate the expectations coming from a stochastic differential equation. Oh yeah, that sounds fun. Um, it might be easiest to do so with the equivalent description with a partial differential equation. I would say we also just care about non-stochastic partial differential equations. Um, there's a recent thread on Zulip. A new person to Lean was asking, what do we have for partial derivatives in Lean and in MATLAB? And some people chime in and say, well, we have everything we need. um, but then Kevin Buzzard says, well, what we have is we have a bunch of people who are asking about partial derivatives in Lean, and we have the foundations. And we can definitely say, well, we have the most generic Frechet derivative, but we don't necessarily have people who have worked out this is how you define a partial derivative for this kind of scenario. And this is how you would do some proofs with that, because you need to take the general form of the Frechet derivative, make it specific, specialize it to all sorts of cases. In thermodynamics, like Maxwell's equations, Maxwell's relations, excuse me, Maxwell's equations, Maxwell relations, so much in fluid mechanics, Navier-Stokes. Okay, these things involve um, partial differential equations. Tying this to stochasticity definitely sounds like fun stuff to do in Lean, because Lean really shines when the math is particularly complex and challenging. And um, but okay, if you're going to connect that from theory and these idealized math structures to the computations, it's going to take a lot more work than just doing it purely in mathematics. You'll have to be thinking about bridging the gap from the non-computable math ideas to the computable functions that one would use to implement these over a grid, a discretized grid or a mesh. For example, if you're going to do computational fluid dynamics or heat transfer or something like that. Plus integrating with stochasticity. So before doing that, I would do coin flips and expectation proofs about coin flips, and then simulations about these. And ooh, it'd be really fun if we could simulate a Gaussian distribution of that, and then prove that in expectation we would see a Gaussian distribution of heads and tails counts, for example. Yeah, and things are a lot of work. But I think that's the beauty of Lean and MathLib in general is we work together, we build things. It's about being focused and deciding what you're going to do first. Like pandas data frames, okay? It's not a really glorified type of thing to say, oh, I'm going to make a slightly different structure than an array in order to do stuff. But if someone goes and builds that next little thing, then it can get incorporated somewhere into the Lean ecosystem. And now people have a new thing available to them. They can build stuff on top of it. And you can prove that everything is correct. So we start with simple things. We try to strategize how we're going to do that. I mean, like, look at us. Like, we've been spending a lot of time trying to get molecular dynamics working, and we're doing energy calculations, the very first step. But we take our time. We're confident that when we build this, we'll be doing something unique, because that's what it means to write code in Lean and write programs that are formally verified scientific computing programs. Um, One needs to think carefully. And if you're a PhD student or an undergrad and you have an advisor and you're thinking about projects to do, you need to talk with them about what might be publishable. Doing something in Lean is intrinsically publishable, I think, in a lot of our areas, because we're bringing something from outside of chemistry, from outside of high energy physics, from outside of that field into this. And that is novel and interesting. And I think there's papers to be written about that and so on. We, though, however, struggled. We submitted to 2 different chemistry journals, and they got desk rejected, saying it's out of scope, before we found that one would take our first paper on formalizing chemical physics, because they had a scope for their journal, and the scope doesn't include formal methods, because no, it's just not in scope for these domain journals. And you can think about what you want to do, because there's also journals on theorem proving and on interactive theorem provers. And so there could be papers to write for those kinds of journals exploring applications of the tools in a domain area. But the audience is going to be different. You wouldn't spend all of your time teaching what is a theorem proof assistant. You would spend way more time teaching what is my domain of chemistry or high energy physics or something. We spent all of our time making it a tutorial to formal methods in general and so forth. So, but in general, like, there's also just stuff to contribute to this. As you get engaged on Zulip and learn how to do these things, people need to write proofs about string operations and proofs about list operations and ways to just use these tools that work better and more conveniently. And the more we can do with that, the more tools everybody has to keep building. And another question, how do we, apart from recursion, do we repeat a block of code using a sort of for loop in Lean? You can. This is referred to as do notation. We referred to that before. And the understanding is, my understanding is, if you want to write proofs about a thing, it needs to be more in a functional style rather than an imperative style. So moving into do notation makes writing proofs about it a lot harder, but you can get the calculations done. And I think the conclusion you need to draw, the pros and cons of the approach. And you're seeing what we're seeing with, we did implement a double for loop, basically a nested for loop in our LeanMD energy calculation. We implemented that, and it was awkward. And it's slow because it's not necessary. And we implemented it to be a tail recursive too. I think some of it is because the structure is not able to take into account other things. And I'm still very hopeful that we can change our data structure from a list to an array and get efficient calculations out and still write proofs about it. But we'll have to figure out how to do that. Ooh, okay, wonderful question. And this is going to be the last question. We're going to end on a really good high note here. We can show how Lean can make proofs from, for example, assumptions in physical chemistry to some deduced formulas that compare with data. What about going in the reverse direction for theory discovery? You have some phenomenological formula that fits data, and you want to find the minimal set of axioms from which it is derivable, I guess, given some general knowledge. I'm going to pull open our paper. So what got me started in all of this, actually, was a collaboration with IBM. Let me get the paper out, and then we'll talk about it. About 5 years ago, what got me into theorem proving in the first place was a collaboration with IBM. In particular, big influence from conversations with Christina Cornelio. She's now at Samsung, PhD in math, expert in logic, computer science, different types of formal methods and proof systems. And our idea was, can we have a generative kind of machine learning model that proposes equations, and then have those equations be generated from data and see if they agree with that data. So we have a sense of, are these accurate equations? Okay. we can do this all the time by generating, that's sort of what machine learning does. You generate some model for some data and you check whether it's accurate or not. So in this paper, we wanted to also bring in this question of derivability. And so the workflow is you send in data, you have symbolic regression, which generates equations. So each hypothesis is going to be a nonlinear equation that fits the data. You pass this into an automated theorem prover. It can't be lean in this case. No, I mean, it can be lean if you have an automated way of generating the proofs. But essentially, we didn't want to produce this proof goal and then need a human to write the code for this. So we did this not using lean, we were using Chimera X. It's a different theorem prover that works automatically. And we run that, generate a proof of this, or generate a disproof saying that it is not possible to do this. And this was a first order logic type problem in the most complicated that we did, which is undecidable. So sometimes we get timeouts, which may be because of inefficiency of the reasoning algorithms or other reasons. But the general idea is here is we're combining the data with and fitting to the data with hypothesis generation and checking against a fixed background theory. So that's where it's a different question from what you were asking. You were saying, can I find the minimal set of axioms from which it is derivable? All right. That would be a different question than the one we had set up. It's tricky to think of, let's propose new axioms, let's propose new premises, but this has been my headspace a long time because I am thinking about those things. Could we have ways of generating premises? You need to watch out though, because it's easy for you to generate your conjecture as a premise, and now it's a really simple set of axioms. So you have one formula that follows from one axiom. It's just a complicated axiom, right? Because it's in the shape of your conjecture. Would we need to have many different formulas and find in common which of these can be deduced from them? So I think there are lots of great opportunities in that respect. We do need, and I believe that lean can play a big part in that. It's related to auto-completing proofs. So let me pull open a slide from lecture one. We talked briefly, we didn't actually have a full lecture on using AI to generate proofs, AI for theorem proving, but that's an area of constant study. Here's an older paper where people trained a language model based on the database of math proofs in MATLAB 3, and then asked it to predict the next word in the proof. Lean checks whether the expected proof steps are correct, and they used a Monte Carlo tree search algorithm in combination with all of these things to generate lots of different attempts. And after it attempts many different kinds of proofs, if Lean tells it any of these are correct, well, then you know that it's true. And these types of things are really great for checking the syntax, okay? And if you're interested in machine learning for theorem proving, there's a separate Zulip channel on that where people are talking about this all the time. Alpha Proof just came out a few weeks ago from Google. I mean, it's not out, it's still under wraps. There's DeepSeeker Proof, which is an open source one that came out last week. And these can solve Math Olympiad type problems that have been formalized already. The challenge for scientists is we also need to formalize the theorem statement. We encountered this in the first lecture. We have a plane flying in which direction and so forth. Okay, I mean, there's multiple ways to write the theorem statement down, and some of them might be wrong. And that's a semantic question. So there's lots of interesting and challenging questions about how we deal with semantics and what ways can we build checks and balances into that. Are there ways to use Lean to do that? Are there other external validating ways to use data to do that? Lots of different directions. We're exploring those, but not nearly as far along in those directions in order to share some of the stuff. Probably next year, though, we'd be sharing what we've been exploring in those spaces too. So, yes, an AI autocomplete of the result given the premises is what I would say. AI should be able to autocomplete a proof connecting in a result to the axioms. AI autocompleting the axioms given the result, well, it won't quite work that way, in my opinion, is because we have constraints on the axiom systems, and we need to bring in our values about those in some way, because nobody's checking whether axioms are correct or not. We need to check those somehow. Occam's razor is one way, to aim for simplicity, but you would still need to define that specifically somehow. Like what does it mean to have something specific? Is it better to have 5 first order formulas or one higher order formula? Which one of those is better, for example? I guess I would pick the higher order one. But at what point do we stop? Can I just write my conjecture as my hypothesis, my assumption, and then do that? That obviously goes too far. But I think if we started working on that, we'll start discovering what works, what doesn't work, especially if there's a specific science domain that one can dig into to get validation, because this, that's going to guide us. We wrote a proposal to do this in an organic chemistry application that I think if that get funded, really excited to dig into that, because it'd be simple. We wouldn't actually need all the fancy, complicated stuff of lean, and that might make it simpler to analyze if we're just dealing with a simpler logical context, for example. But yeah. Thank you everyone for the questions, and please join us next time because we have Tomas Scriven teaching us all about silane, which is I'm really looking forward to.